Section 2.3 is on page 160 in the book, and 168 if you're using the PDF. Talks about the limit laws. Now, the limit laws are not that complicated, since pretty much you could switch the wording on any type of operation which is not allowed in math or anything other than a limit. Suppose C is a constant, and the limit as x approaches a of f of x, and the limit as x approaches a of g of x exists. That means the limit from the left and the right of a of f of x is the same value. We don't know what that is, and we don't need to know what that is. So the limit laws are, if you're taking the limit of two functions that are added, you could take the limit of each and add the result. So the limit of the sum of two functions is the sum of the limits of the two functions. The limit of the difference, if you take in two functions, subtracting them and take the limit of that, you could take the limit individually and subtract the results. If C happened to be a constant and you take in the limit, you could ignore C, take the limit of the function, then multiply the result by C. Very simple. And if you have two functions multiplied, you take in the limit of the product, that would be the product of the limits. The limit of the quotient is the quotient of the limits. And the wording could switch on anything. The limit of a power function is the power function of the limits. Now, these are two special cases. If y happened to be a constant, the graph will look like this. If you take any value a, you approach from the left or the right, y will always be 3. So the limit of the constant is always the constant. And this one comes up as well. If you have y equal 3x, if you have a straight line, whatever x is approaching, y is approaching, because we said if y equal x. If y equal x, if x is approaching 5, y is approaching 5. If x is approaching 3, y is approaching 3. Those are two special cases. And here, limit of a power function is pretty much, you just plug that in, that'll be a to the n, because that works identical to this. Limit of a root function, you plug it in, and limit of the nth root of a function is the nth root of the limit of the function. So here, the part they left out, that's the limit as x approaches a of x to the n, and we just said by 8 right there, that is a to the n. And here, that is the nth root of the limit as x approaches a of x, and again by 8, and what allows us to do this step is 6. So the rules, you really don't have to remember them by number. You just need to look at the numbering just for the first 2 homework problems. But on a test, I will never ask you to justify like they do right here. So this is just to make sure you understand this. The couple of problems here, this is on page 176 in the book, 184 if you're using the PDF. In the following exercises, use the limit law to evaluate the limit. Justify each step by indicating the appropriate limit law. You just have to mention the number. Again, this is not on a test. I'm not going to give you this table on a test, and I'm not going to ask you to really justify these steps, but for the homework, it's important that you just get the logic out of the way. This will be the limit as x approaches 1. You know what? I don't know why I have all the space in the world. There we go. Of x cubed plus 3x squared plus 5 divided by the limit as x approaches 1 of 4 minus 7x. And what allows me to do this division, where is it? Quotient, that's property 5 right there, or law 5. And now taking the limit of the sum and the difference. That would be x cubed plus the limit as x approaches 1 of 3x squared plus the limit as x approaches 1 of 5. What allows me to do that, limit of the sum of two functions, this is by 1 and this is by 1. And the denominator, that's the limit as x approaches 1 of 4 minus the limit as x approaches 1 of 7x. And this is 2. Limit of the difference is the difference of the limits right there. And now that would be 1 cubed plus 3 times the limit as x approaches 1 of x squared plus 5. And what allows us to do that? For x cubed, I used 9. I just substituted that in. And for the constant, that was 3. And limit of the constant is the constant. That's 7. As for the denominator, that would be 4. That's by 7. That's a constant. Minus 7 times the limit as x approaches 1 of x, and that's 3. And the last step, I would say that is, as far as limits, 1 cubed plus 3. Well, I know that 1 cubed is 1. And here I'm going to get 1 squared. What allow me to do that is, was it 9? Yeah, 9, substituting. And this is a 5, 4 minus 7, and limit as x approaches 1. You plug it in. You could call that 7. You could call that 9 as well. Either 9 or 8. It doesn't matter. Notice those are the same. So let's say 8 because that's x. And simply, what do we get? 5, 8, 9 divided by 4 minus 7, which is a negative 3. Now, what's the alternative? I can make a table, and I could put points to the left of 1 and to the right of 1. And guess what? I'll get the same result. This is going to be a quicker way. Why is that? Because once we're done with these two examples, when I say find that limit, you could just plug it in. Just negative 3, huh? And that will be simply 9 divided by negative 3, which is 3. Same deal here. For now and for this problem only, we're going to say this is the limit as x approaches negative 1 of 9x plus 1 squared. And what allows us to do that is 6. And that's going to be the limit as x approaches negative 1 of 9x plus the limit as x approaches negative 1 of 1, and that's property 1. And that's going to be 9 times the limit as x approaches negative 1 of x plus a 1. What allows us to do that, this is the constant part, that was, I believe that was 3. Yeah, that's 3 right there. And limit of the constant is the constant, that's 7. And that turns out to be 9 times negative 1 plus 1. And what allows us to do that, substituting in x, again we said 7 or 8. Let's go with 8 because you substituted that in. And now it's simply negative 9 plus 1, which is negative 8 squared, and that is 64. Again, this is a bit tedious, but it's good to know that you could use those. And of course, after this section, if I say find that limit, guess what? You throw the negative 1 in, and you get negative 8 plus 1 squared, which is 64. And I know you're thinking, wait, can I do that? Well, it's right there actually. We have a shortcut. So how do you find the limit? You plug in numbers, you make tables. If we're taking the limit as x approaches 5, you pick values to the left of 5 and to the right of 5. That's how we find the limit. How would a limit exist? If the limit from the left and the limit from the right agree, you reach the same value. How would a limit not exist? If the limit from the left and the limit from the right do not agree. Anytime you're allowed a calculator, you're asked to find the limit, you could use it. Limits from the left, limits from the right, but that's a lot of work. We have a shortcut, something we're going to use all throughout. And we're going to force this one. On certain parts of the homework, on the exam questions, it's going to say find the limit. A calculator is not allowed. So, if f of x happened to be a rational function, a polynomial function, radical function, exponential function, logarithmic function, or a trig function, then if I'm taking the limit as x approaches a of f of x, I simply substitute that in. Again, if f happened to be any one of those. If I get a number, I'm done. That's the limit. That's a shortcut. That's kind of like this problem. 84. I'm finding that limit. I plug 1 in because that's a rational function. I get negative 3. I'm done. No need to do all of this work. I'm looking at 86. That's a power function. So that's a polynomial, right? If you FOIL that out. So how do you find the limit? Shortcut, you throw negative 1 in. You get 64, you're done. No need to pick points. And no need to go and justify everything. If I get a number over 0, if I get any number over 0, then my answer is either positive infinity or negative infinity. There I have to do a couple of points, and I'll show you how to do that. And you don't need a calculator for that. And if I get 0 over 0, which is going to happen most of the time, that's where the algebra is going to come in very handy. Now, just to keep you posted, when I say a number over 0 is positive or negative infinity, let me show you really quick. If I take the limit as x approaches 0 from the left of 1 over x. So it's not really 1 over 0 is undefined. The reason it's undefined because it is infinity. That's what it is. For now, let's play with that. If you take the limit as x approaches 0 from the left, and this is be really quick. If I pick negative 0.1, 1 divided by negative 0.1 is negative 10. If I take negative 0.01, 1 divided by negative 0.01 is negative 100. Do you see this is going to approach negative infinity very quickly? And if I go from the right, if I pick a positive 0.1, 1 over 0.1 is positive 10. 1 over positive 0.01 is 100. So that's why you get plus or minus infinity depending, are you approaching 0 from the left or the right? And 1 over infinity, again, this is not something you use in algebra, but think of it this way. Not really 0, the limit as x approaches 0, and not really infinity, the limit as x approaches infinity. If I have 1 over x and I take 10, 1 over 10 is 0.1. I want x to approach infinity. So if I take 100, 1 over 100 is 0.01. If I take 1,000, 0.001. So you notice this number is going to get smaller and smaller, eventually you're going to reach 0. And the only number that you could say plus or minus is identical is 0. Plus or minus 1 are 2 units apart. Plus or minus 4 are 8 units apart. But if you say I have a plus or minus 0, that's 0. And that's where it is. So this is going to help you when you figure out this shortcut and play with those. So on 88 and on, oh, you got to give me a second. I forgot the directions. What do you know? Okay, in the book they have different directions. Here they say substitution. Here they say show. Here, to you, it should be pretty much find the limit. and we're going to follow the shortcut rule because that's really where they're going, and we want to get that out of the way. So find the limit. Well, shortcut, I substitute a negative 2n. That will be 4 times 4. That will be 16 minus 1, which is 15. Done deal. And why is that? That's a polynomial. This is an exponential. Find the limit. Substitute the value n. Every time you substitute a value, I suggest you use parentheses so that if you make a mistake, I know what went wrong and I can give you partial credit. And here again, this will be, well, you know what that is, by the way. ln of e to the 3x is simply 3x, right? They undo each other. So that's going to be ln of e to the 3 times 3. That is ln of e to the 9, but those undo each other, and that's a 9. Property of logs. Okay, I'm not sure how long I need, but here we go. We'll see if that works that way. Okay. Okay, what just happened? There we go. Oh, it stretches more. All right, well, let's see how this works. No, it doesn't. Okay, well, what do we get here? Here we throw a 2 in. We get 2 minus 2, that is 0. And 4 minus 4 over 0. Hey, so the first 3 problems we got a value, we were done. And that's because the functions match each one of those. Now we got 0 over 0, and that's going to happen a lot. 0 over 0. What can you do for rational functions? Well, the traditional. We could just factor. The top is x minus 2. The denominator is x into x minus 2. And what happens? Those two cancel out. Now I'm taking the limit as x approaches 2 of 1 over x. And once you cancel a factor out, you throw 2 in and you get 1/2. Again, the alternative to this is to make the tables. The alternative to 88, 90, 92, 94, 96 is to do the tables. And that's highly not recommended if you could avoid it, because as you see, it doesn't take time at all. It's a lot quicker to do algebra, but you have to use algebra regardless. It's not an option. And if I get to number 96, you say, okay, well, let's see, what's that? That is, if you put 0 and you get 1 squared, which is 1 minus 1, that's also 0 over 0, which means I need to manipulate that. Well, how are you going to do that? Pretty much as straightforward as it is. FOIL. Now you have to write the limit every time. Those cancel out, and I notice I have 2h plus h if I factor an h out, and those cancel out. And again, once I cancel the 0 factor, I substitute 0n and I get 2 plus 0, which is 2, and there it is, done. And if I look at the following, throw a 0 in for h, I'll get 1 over a minus 1 over a, that's 0 over 0. Here, this is a complex fraction. The quickest way of simplifying this is to find the LCD for the top and the bottom combined. The LCD for the top and the bottom combined is a into a plus h. If I make sure that each of those is over that LCD, each of the top and the bottom, then that will transform the complex fraction into a single fraction in which I could ignore the denominator altogether. That's algebra. And simply, that's a. Make sure you copy that sign with parentheses. One times a plus h is a plus h, and here you have ha into a plus h. limit as h approaches 0, and the reason I'm not distributing the bottom because I'm trying to cancel out the 0 over 0 factor. No point in distributing the denominator because then you'll have to factor it. And what do you notice? I'm left with the limit as h approaches 0 of negative 1 over a into a plus h. And we get, if you substitute 0 in for h, that's negative 1 over a times, and if that's 0, that's just a, and that will be negative 1 over a squared. And there it is. So, a lot of algebra is coming your way. Actually, when students ask me, how hard is calculus? My question is always, how good is your algebra? You're going to use most of the algebra that you learned. All right, now we get to these two. Let's see how that works. If I want to take the limit as x approaches 1, well, that's 1 cubed minus 1. There. Well, that means I have to factor the difference of cubes. If you recall, a cubed minus b cubed is a minus b into square the first, square the last, multiply those. This is always positive, and this sign is always the opposite of that. Something that you have came across in algebra. So that's x minus 1, square the first, square the last, multiply those. This sign is always the opposite of that. And the difference of squares is simple. And once I cancel those, I restart the shortcut from scratch. So if I throw 1 in the top, we'll get 1 plus 1 plus 1. And in the bottom 1 plus 1, which is 3 over 2. So the only time you don't include the limit is when you substituted the values in. Notice I don't write the limit only at the last step. And here, if I let x approach negative 3, negative 3 plus 4 is 1. Square root of 1 is 1 minus 1, that's 0 over 0. With radicals, you are limited. It's a good and bad news, I suppose. The bad news, you have to rationalize. The good news, you will always know that you're going to rationalize. So you know exactly what to do. So you multiply by that conjugate. Exactly what you see with the radical, top and bottom. But you switch that sign. That's conjugate. What happens, that enforces the top to be the conjugates, which are pretty much the first squared minus the second squared. So you get the first squared. Well, the first squared will cancel the radical. 1 squared is 1. And the denominator, you're going to get a big mess, but it's okay. Few steps. And that will clear. And that will be the limit as x approaches negative 3 of x plus 1. X plus 4 minus 1 is x plus 3. And you might be wondering, how come I'm getting things to cancel every time? Well, the 0 over 0 is going to guarantee that because you're getting the same factor. So this cancel with that. I'm looking at the limit as x approaches negative 3 of 1 divided by the square root of x plus 4 plus 1. Throw negative 4, negative 3 in. You get the square root of 1 plus 1. Well, that is simply 1/2. So on these problems, you're not going to be allowed a calculator. You're going to have to show the work that I'm showing you. And these are taking the cases. This is the third case. If you throw negative 2 in, again, even though it says from the right, try negative 2 anyways. Throw negative 2 in. That's 2 times 4, that's 8, plus, oh wait, yeah, 2 times negative is negative 14 minus 4 over 4 minus 2 minus 2. That turns out to be negative 18, negative 10 over 0. And according to our shortcut, if you get any number over 0, the answer is either positive or negative infinity. Let's see which one is it. How are we going to figure that one out? Well, what we're going to do, we're going to factor the top and the bottom if we can. The bottom factors into x plus 2, x minus 1. And the top factors into, let's see, 2x and x, a 4 and a 1. We want a positive and a negative. Let me see if that's true. Okay, so nothing cancels out because I didn't get 0 over 0. I got negative 10 over 0. We know that. So we're going to say this is the limit as x approaches negative 2 from the right. Now let's see, where is the 0 in the denominator coming from? The 0 in the denominator is coming from this factor. So what we do, we split up. Remember, we could do that according to the limit rules. And you could always do that. Well, here we already know. If you throw negative 2 in the top, you're going to get, we said, a negative 10. And if you put a negative 2 right there, negative 2 minus 1 is negative 3. And here, I'm picking approaching negative 2. Well, it's really simple. I know this is going to be either positive infinity or negative infinity. All what I have to do is use one test point without a calculator. If I pick a point approaching negative 2 from the right, so let's say negative 1.9, this will be 1 over negative 1.9 plus 2 is positive 0.1, which is 10. So I know this is positive infinity. Now, this is going to be positive. If you take infinity and multiply it by a positive, the answer will be infinity. If this was negative, that would have been negative infinity. Think of infinity. Don't think of infinity as infinite. Think of infinity as a very large positive number. If you have a very large positive number, thousands of trillions of billions, or billions of trillions, if you multiply that by a negative, that becomes a negative. So that's the only reason we do this work, to figure out if it's positive or negative. Again, if you have a million, if you multiply by negative 1, that's negative a million. Same deal here. I'm approaching 1 from the right, so the top is 2 plus 7 minus 4 over 1 plus 1 minus 2. That happens to be 9 minus 4 is 5 over 0. Again, if I make a calculation in algebra, you just fix that. That's not an issue. Sometimes I do that. So I know the answer again is either positive infinity or negative infinity according to this shortcut. So I go and say, well, all right, let's see. I'm trying to figure out where the 0 is coming down in the denominator. Obviously, there must be an x minus 1. For the top, well, it's the same problem, right? In case you didn't notice. Same problem, I mean, it's that problem. Well, here, what's causing the 0 in the denominator is this factor, but according to the limit laws, I could say, look, so I'm using the limit laws backwards to my advantage. So here, I'll say if you throw 1 in, we already calculated the top. Wait, it's a 5. Oh yeah, it's a 5 because here then it's approaching 1. 5 over, and if you put a 1 there, 5 plus 1 plus 2 is 3. Okay, so it's positive. That's good. Here, I just need one value. Again, I know this is going to be 1 infinity or negative infinity. If I pick a point to the right of 1, let's say a 1.1, and put it in there. 1.1 minus 1. 1.1 minus 1 is 0.1. That's 10. That's also positive infinity. And when I multiply a positive times infinity, I get infinity as well. And if this was negative, I would have gone negative infinity, and so on and so forth. And the last part is just to make sure you understand how the theory works. This is really not that bad at all, but you want to make sure that you see how it works. This is not. Okay, let's do it again. There we go. Now, it says, assume these are true. this is enforcing the limit laws. Well, isn't this limit of the quotient is the quotient of the limits? And I could take the limit of each of those individually. By now, hopefully you're comfortable with those. And according to what I have up there, I see g of x, and I see f of x. Well, I know what those are. That is a 4. Oops, I'm sorry, that's a 9. And limit of the constant is the constant, that's a 1. I took the negative up front. Over, and the yellow is a 4. And that gives me 8 over 4, which is 2. There. And wouldn't this be it froze for some reason? Wouldn't this be limit as x approaches 6 of h of x cubed over the limit as x approaches 6 of 2? Now, I know what you're thinking. Can't I just do this? Can you? Yes, you can, of course. And you really don't have to show this. And here, you could have just went straight and plugged things in. And what would that be? Well, I know what this is. This is the green, right? H of x, it's right there. So that's a 6 cubed divided by 2, and whatever that is. Right? That's 6 times 6 times 6. 2 divides 6 3 times. So that's 36 times 3. I don't know what that is. 108. Okay. And here, isn't this limit as x approaches 6 of x? So it's easier to really follow the rules. This way you see how it works. This is simply plug it in. And this is the green, right? H of x, that's a 6. And that's 36. Okay, very important. I just make sure that you know how to reinforce the limits. And if I take this, that's going to be what? Limit as x approaches 6 of f of x, limit as x approaches 6 of g of x, minus the limit as x approaches 6 of h of x. And that is, so f of x was the yellow, g of x was the green, the blue, and the green. And that would be 36 minus 9, which is 27. Okay. And a couple more to go. We're almost done. It says, in the following exercise, use a calculator to draw the graph. Well, you're going to graph this. That's simple to do. If x equal 1, y equals 0. So this is a cubic function shifted 1 unit down. So it should look like this. Like a parabola. And minus that parabola. There we go. But we only want this when x is less than 0. We only want that piece of the graph. And we have another function. And this second function is y equal 1. Y equal 1 is one of these lines. When x is bigger than 0, there's x equals 0, not included. X is bigger than, so you're only looking at this piece of the line. There it is. And then they say, hey, what's the limit as x approaches 0 from the left? By the way, I could use the graph and I could just use the functions. Let me show you. If I'm using the graph, if I'm taking the limit as x approaches, this is g of x, of course, 0 from the left, there is 0. If you're approaching 0 from the left, I'm going to use this color so I don't mess up the graph. 0 from, there's 0. Coming from the left, you're along this purple path. And guess what? Actually, no, let me stick with purple. Isn't that approaching -1? From the graph, there it is. And if you're picking 0 from the right, there's 0 coming from the right side. Isn't that a 1? You could also do this if you wish. I'm going to use the purple if x is less than or equal to 0. And I'm going to use the green if x is bigger than 0. That's one way of doing it. Another way of doing this same problem, and let me show you really quick. Here they want us to use the graph on a piecewise function, but I want to make sure that you are comfortable with this second piece as well. Actually, let me put it right there. Here, and let me put this right here. If I'm not using the graph, notice. If I'm not using the graph, notice I'll be taking the limit as x approaches 0 from the left. Well, look at g of x. G of x is one of two functions. If x is approaching 0 from the left, aren't you right there? So must use the x cubed minus 1. And algebraically, you substitute 0 and that gives you 0 minus 1, which is -1. And there it is. And if you're approaching 0 from the right, as x approaches 0 from the right, isn't this to the right? You must use the 1, and the limit of the constant is always the constant. So you could do this both ways, algebraically or graphically. You should follow directions. But I'm just pointing out that this does come up a lot. And there it is. Now we get to the last idea of this section. It's called the squeeze theorem. If you took AP Calculus in high school, this is called the sandwich theorem. So simply, ST. You'll nail both, whether you learned in high school or in college. Every time you have to use this, every time you use this, you have to state by the sandwich theorem or by the squeeze theorem. That's why we call it in algebra, in calculus. So it says, if I'm looking at g of x, and g of x is bounded by two functions. So f of x is a function that's less than or equal to g of x, and h of x is a function that's bigger than or equal to g of x. If I take the limit as x approaches a of each of those, that's valid. So the limit as x approaches a of g of x is unknown to me. I don't know what that is. But I know this right here is L, and this right here is L. Well, now we're talking about algebra. If you have a number or a value that is bigger than or equal to a number and less than or equal to that number, the only conclusion is that, or the only solution is that, is the number itself. So if I told you x is less than or equal to, bigger than or equal to 3, less than or equal to 3, there's only one solution there. If you put this on a number line, that's the only solution that satisfies this inequality. And that's what the squeeze theorem says. So I look at something like this. If I substitute 0 in, that's 0 times the sine of 1 over 0. We have a problem. We don't know what to do with that. But I know trig. I know that x squared sine of 1 over x. I know the biggest and the smallest a sine could ever be. The largest a sine could ever be is a 1, the amplitude, and the smallest it could ever be is a -1. So I know that x squared sine of 1 over x is bound between x squared and negative x squared. I'm trying to find the limit as x approaches 0, so now I take the limit as x approaches 0 of each of those. And you could do that, that's allowed. And what I notice, this is the limit as x approaches 0 of negative x squared. This is the limit as x approaches 0 of x squared sine of what, which is something I don't know. And this is the limit as x approaches 0 of x squared. But if you substitute that in, isn't that 0? And isn't that 0? So what's the conclusion? Therefore, the limit as x approaches 0 of x squared, which I do not know, but I am certain it's 0 because it's bounded above and below by that number, by the squeeze theorem. And that's pretty much it for this section.